In this video, we are going to see how to design a voltage regulator PCB to get 5 volts and provide 3.3 volts. The 5 volt is provided via a USB-C connector, which you can see it here. Then this voltage is passed to a voltage regulator called LF33, which gets 5 volts and gives us 3.3 volts. You can see it in the middle of the PCB. It is manufactured by ST Microelectronics company. You could also see decoupling capacitors, I mean C1 and C2. One of them is SMD and the other one is SMD electrolyte capacitor. We can also get the voltages from the phonics contacts, which you can see here. Both 3.3 volts and 5 volts are available, and GND pins are also available and provided. Next, we are going to provide the power for our PCB. You could do that via your phone charger. This is the thing that I'm doing because it has USB-C cable. So you need to make sure you can provide USB-C cable to power your PCB. Then plug in the phone charger and then connect it to your PCB. The red light indicates that the power is provided sufficiently for our PCB. Now we are going to evaluate the performance of our PCB. We need a multimeter, then we measure the voltages. First, I measured 3.3 volts and it works properly. And then 5 volts. It's a little bit higher than 5 volts. It is related to USB-C and the phone charger. It is not our fault. Then we could connect these phonics contacts to our PCB, and then we could tighten the wires via screws for future purposes. And by the use of these contacts, still our PCB works just fine. And at the end of the day, this is how our circuit and PCB looks like and works properly. Let's see how to design it in Altium Designer. We first check how to provide the schematic for this PCB, and then layout and routing, and see how to prepare this PCB for manufacturing. This is the schematic for our voltage regulator. As you can see, the schematic is relatively simple. This symbol is for USB-C connector. This is a 6-pin USB-C connector. It has 6 pins, 2, 4, 6. These 4 pins are mounting pins and they shouldn't be connected to anywhere necessarily. So I've used these directives, which are called generic no ERC. So you are telling the Altium Designer that I don't want to connect these pins to anywhere, and then you will not be faced with any errors. It has 2 VBus pins and I have connected them together and then connected them to 5 volts. In fact, 5 volt is being provided by USB cable, and then that is connected to our USB-C connector. If you are wondering why this USB-C connector has 2 pins of each pin type, the answer is USB-C accepts cables to be connected to it with 2 orientations, and it works properly and without any problem. That's why it has 2 pins from each pin type. These GND pins are also connected together, and then I've connected both of them to GND. So there shouldn't be any problem as well. But look at these CC pins. If you pull down these CC pins to G and D via a 5.1 kilo ohm resistor, you are signaling that this circuit, that its power is provided via this USB-C connector, is a sink and it's not the source. In other words, this circuit gets charged and it doesn't charge any other circuits. In order to signal this situation, you need to pull down CC pins to ground via 5.1 kilo ohm resistor. There is an important note here that you should consider, that you are not allowed to connect these CC pins together and then connect them to G and D via only one 5.1 kilo ohm resistor, because this configuration is so error prone and your circuit may not work properly. So always use two set of resistors to connect CC pins to G and D if you want your USB-C connector to work as a power sink. I've also provided an LED in series with a 303 ohm resistor so that whenever our circuit is powered properly, in other words, power has transmitted to our circuit properly, this LED is turned on so we can see that our circuit is on. This is red LED and this is SMD resistor and its package is 0805. And I've connected it to 5 volts and the cathode of the LED to G and D pin. And here is our LF33 IC, which is our voltage regulator. This is the heart of our PCB. It has 3 pins: input, output, and G and D. G and D pin is connected to G and D directly, and this IC gets 5 volts and provides 3.3 volts for us. This is exactly what we need. You should also use input and output capacitors to reduce the noises that exist in your circuit. The input capacitor is a 100 nanofarad capacitor. I've used SMD 0805 package for this capacitor. This is our input capacitor. And the output capacitor, which is 2.2 microfarad capacitor, which is larger than input capacitor. Its package is SMD. In fact, it is an SMD electrolyte capacitor, and it perfectly removes ripples and extra noises from our voltage, which in this node which exists here. So we could get a good 3.3 volt voltage from this node. And in the end, there are 2 connectors. I've used phonics contacts for these connectors, and one of them provides 5 volts and G and D, and the other one provides 3.3 volt and G and D for us. So by plugging USB-C cable to our circuit, we can get both 5 volts and 3.3 volts. And there is an LED that indicates that the power is provided to our circuit properly, and a D-pack LF33 IC to convert 5 volts to reliable 3.3 volts. And this is the overall view of our schematic. Next, we are going to see how to place components on PCB and do the layout and routing. Now, it's time to see how to design our PCB for the schematic. This is the 2D view of our PCB, and here is the 3D view of our PCB. This is our USB-C connector, as you can see it here. And these resistors, R2 and R3, are connected to the CC pin of the USB-C connector. Let me split the screen in vertical form and open the schematic. Here we can see both the schematic and PCB simultaneously. These R2 and R3 resistors, which their value is 5.1 kilo ohm, can be seen here. And U1 is our voltage regulator, which is LF33. C1 and C2 capacitors can be seen here. These are decoupling capacitors. R1 and D1 are resistor and LED, which indicates that power is delivered to our PCB. And these are our connectors, which are J1 and J3 in our schematic, which we can get the voltages from these nuts. I've placed a polygon all over the PCB and its net is GND, which you can see it here. In order to be able to explain the PCB properly, I will delete this polygon, and when the explanation finishes, I will press Ctrl Z and recreate the polygon pour. As you can see, CC pins of the USB-C is connected to corresponding resistors, and the pins that should be connected to GND is left floating for now, but when routing signal tracks and power supply tracks finishes, we place a polygon all over the PCB to connect the GND pins of the components together. This is true for the GND pins of the USB-C connector as well. The 5-volt pins for the USB-C connector are connected together via a polygon, as you can see it here. Then this 5-volt is also connected to this connector's pin directly, so we can get the 5-volt from this nut here as well. It is also connected to one pin of the resistor, which will be connected to our LED. This small plus sign here indicates that this pad is related to anode of the LED, which is indicated by D1. This 5-volt is also connected to one of the pins of the voltage regulator, as you can see here. And a decoupling capacitor is also connected to our voltage regulator, and GND pad is left floating for now. And here is our voltage regulator, and after getting the 5 volts, it creates 3.3 volts, which is connected to a decoupling capacitor, which is relatively large, and its value is 2.2 microfarads, and the GND pin has been left floating for now. And then this filtered voltage is connected to one of the pins of this connector, so we can access this voltage. Our name and logo is also placed on the PCB, and the edges of our PCB is determined by lines on the keep out layer, so the borders are clear. And after that, we have placed a polygon all over the circuit to connect the GND pins of all the components. Here you could see the bottom side of the PCB as well. And now our circuit is ready to be manufactured. You need to call your PCB manufacturer to see what files they need to produce this PCB. Next, we are going to see how we will receive our ordered PCB and how it works after components have been soldered on the PCB and it is ready to do the functionality that we expect it to do. Let's see this PCB in reality. This is how I received the PCB from my PCB manufacturer. I ordered 2 PCBs and they are panelized, as you can see. I depaneled one of them and soldered components on it. Now I'm depaneling the other one. Nice. We don't need the panel anymore. And this is how our PCB looks like. The next step is to solder our components on the PCB. I've already done it on the other PCB and you can see it here. Jing. You can compare our PCB with and without the components. You can see the USB-C connector, voltage regulator, and the phonics contacts. The required capacitors and resistors, and this is the bottom view of the PCB. When you are designing your PCB holes, always keep the PCB holes a little bit larger than what is required, because it makes your life much easier when soldering components on your PCB. And at the end of the day, this is how our PCB looks like. I would also like to tell you that the project files are available in my GitHub repository and you can access and use them. If this content was useful for you, don't forget to give it a thumbs up and subscribe to our YouTube channel for more electronics content. Good luck!